Good day. I am Justin Guzman, and this is my presentation submission for the CS4103 subject, where I will be conducting two paper reviews on the subject of deep learning based audio-visual speech recognition, or AVSR system, and compare their methods and results. For this presentation, I will be thoroughly discussing and providing a detailed comparison on the following papers. The first paper that I will be reviewing is Audio-Visual Speech Recognition Using Deep Learning by Noda, Yamaguchi, Nakadai, et al. And the second paper is Improving Audio-Visual Speech Recognition Using Gabor Recurrent Neural Networks by Saudi, Khalil, and Abbas, where both papers utilized different deep learning techniques in achieving an efficient and accurate AVSR system, or Audio-Visual Speech Recognition System. The following is the agenda of this presentation. First, I will be giving a general overview of what audio-visual speech recognition or AVSR systems are, the problem that these systems aim to solve, and the significance of such systems in today's society. Second, I will be thoroughly discussing the deep learning methods and techniques that both papers use and implement in achieving their desired AVSR systems. And finally, I will be comparing the results of both papers and their overall conclusion. But before diving right into the purpose of this presentation, let us first tackle the definition, the problem and the motivation, and the significance of deep learning in AVSR. So, what is AVSR? Audio-visual speech recognition, or AVSR, is a technology that integrates both auditory and visual information to enhance the accuracy and performance of automatic speech recognition, or ASR systems. The basic idea is to combine the audio signal of speech with visual cues, such as lip movements and facial expressions, to improve the system's ability to understand and interpret spoken language. This multimodal approach is particularly useful in scenarios where the audio signal alone may be insufficient, such as in noisy environments, when speakers are at a distance, or when the audio is unclear. Furthermore, the key components of AVSR are the following. First, audio processing. The system analyzes the traditional audio signal associated with speech. This involves techniques from automatic speech recognition, or ASR, that convert the acoustic features of speech into a sequence of words or phonemes. Second, visual processing. AVSR incorporates visual information often obtained from video data. Lip movements, facial expressions, and other visual cues are analyzed to extract features that can aid in speech recognition. Third, integration of modalities. The audio and visual information is then combined at some level of processing. This integration can happen at the level, where the features from both modalities are fused before feeding into the recognition system, or at higher levels, where the outputs of separate audio and visual recognition systems are combined. Finally, recognition and output. The integrated information is then used for speech recognition, generating a more accurate and robust output compared to systems that rely solely on audio data. The primary goal of both papers is to improve speech recognition systems by combining audio and visual data, addressing the challenges faced by audio only systems, especially in noisy environments. By adding visual information like lip movements, the systems can better understand speech when the audio is unclear. This approach is similar to how people use both sight and sound to understand speech, particularly useful when audio quality is poor. The studies use certain deep learning methods and techniques that help the systems to perform well in various conditions, including different noise levels, and with speakers who have diverse speech patterns. The integration of visual data also helps in recognizing speech from different speakers, making the systems more accurate and robust in a range of real world situations. Deep learning is prevalent in audio-visual speech recognition, or AVSR, due to its ability to automatically learn intricate features from raw data, eliminating the need for manual feature engineering. Deep neural networks, including convolutional neural networks or CNNs, and recurrent models like long short term memory or LSTM networks, excel at capturing complex relationships in both audio and visual cues. The end to end learning capability of deep learning models allows them to directly map raw input data to output labels, enhancing their suitability for AVSR, where capturing the temporal dynamics of speech and lip movements is crucial. Moreover, deep learning models, with their high capacity for handling nonlinear relationships, robustly address challenges such as speaker variability and environmental noise. The representation power of deep neural networks, especially in handling sequential information and spatial features from visual data, contributes to the superior performance of AVSR or audio-visual speech recognition systems. Now let us discuss further into both papers and conduct a thorough paper review and comparative analysis. The first topic to tackle are the datasets used in both papers. The first paper uses a Japanese audiovisual dataset, which includes speech data from six male speakers. This dataset comprises of 400 words, including 216 phonetically balanced words and 184 important words from the ATR speech database. A total of 24,000 word recordings were prepared, with each set of words per speaker amounting to approximately 1 hour of speech in total. The audio data was recorded with a 16 kilohertz sampling rate and a 16-bit depth in a single channel. And the visual data was a full frontal 640 by 480 pixel monochrome facial view recorded at 100 Hz. The second paper utilizes a dataset that is composed of recordings from 36 speakers, including 19 males and 17 females, who utter 5 repetitions of continuous and isolated digits. To simulate real world audio conditions, the clean audio recordings are corrupted with additive white Gaussian noise at various signal to noise ratios or SNR, ranging from -10 decibels to 20 decibels. The dataset consists of 14,400 samples divided into 12,000 for training, 1,200 for validation, and 1,200 for testing. Moving forward, I will be tackling the proposed methods and techniques used in both papers. The first paper presents the architecture of the proposed AVSR or audiovisual speech recognition system. The proposed system is composed of two deep learning architectures, a deep denoising autoencoder, and convolutional neural network, or CNN, for the audio and visual feature extraction, respectively. The deep denoising autoencoder is trained to predict clean audio features from deteriorated ones to filter out the effect of noise from the input. The CNN is trained to predict phoneme labels from the mouth area, image inputs to generate the visual feature sequences from the lip motion of speakers. Finally, a multi stream hidden Markov model or or MSHMM is utilized for the isolated word recognition by integrating the acquired audio and visual features. Let us look into each of the deep learning architectures used, starting from the deep denoising autoencoder. The figure in front of you represents a deep denoising autoencoder used for audio feature extraction, as discussed in the paper. This type of neural network comprises of two main parts, an encoder and a decoder. The encoder comprises the input, which is a noisy audio signal, into a lower dimensional representation. This representation captures the essential features needed to reconstruct the original signal while ignoring the noise. The decoder then takes this compressed representation and attempts to reconstruct the original clean audio signal from it. The network is trained using noisy audio as input and the clean original audio as the target output. Through this training process, the autoencoder learns to filter out noise, effectively denoising the audio signal, which is crucial for robust speech recognition in environments with significant background noise. The next deep learning technique that I will be tackling is CNN, or Convolutional Neural Network, and its application in this paper. The model described is a convolutional neural network, or CNN, used for visual feature extraction in the task of predicting phoneme labels from mouth area images. The CNN structure includes several layers: convolutional layers that filter input images to extract relevant features, pooling layers that reduce dimensionality and retain important features, and fully connected layers that classify the extracted features into phoneme labels. The CNN is trained with a dataset augmented with modulated images to enhance shift and rotation invariance, aiming to improve phoneme recognition precision. Phoneme label posterior probabilities are generated by the CNN, which outputs a 40-way softmax function representing the likelihood of each phoneme label at a given time slice. The network is optimized using a multinomial logistic regression objective, aiming to maximize the log probability of the correct labels during training. The final deep learning technique is the multi-stream hidden Markov model, or MSHMM, and its application in this paper. The multi-stream hidden Markov model, or MSHMM, illustrated is used for audiovisual speech recognition by integrating separate streams of audio and visual data. Each stream is modeled using Gaussian mixture models within an HMM framework, and the HTK software implements this approach. Observations at each time step are split into audio and visual streams, and their contributions to the state probabilities are weighted manually, allowing the model to adjust the influence of each modality based on its reliability. The MSHMM's effectiveness is evaluated by varying the audio stream weights while complementarily adjusting the visual stream weights, ensuring their sum equals 1. This method optimizes speech recognition by selecting the weight combination that yields the best recognition rate, thereby exploiting both audio and visual data to enhance performance, particularly in situations where one modality may be compromised. Now that we are done with the proposed methods and techniques in the first paper, I will now discuss the deep learning techniques applied in the second paper. Here is a specialized form of a neural network optimized for audiovisual speech recognition. The network architecture consists of five hidden layers with 1024 units each, employing bidirectional recurrent neural networks or BRNN with long short term memory or LSTM cells. This setup is adept at capturing the complex patterns in time sequence data, such as speech, with a bidirectional approach, processing inputs in both forward and backward directions to maintain context. The use of LSTM cells helps in remembering long term dependencies, crucial for understanding speech dynamics over time. For training and performance measurement, the model utilizes the CTC loss function, which is particularly suited for problems where the timing of the output is variable, like speech. The Adam optimizer is chosen for its efficiency in updating network weights, with a fixed learning rate that ensures consistent learning across iterations. The network on a combination of audio and visual data, allowing it to predict speech more accurately by learning from both modalities. Now that we have tackled the different deep learning techniques used in both papers, let us explore further on the results and conclusions. The first paper assessed the effectiveness of DNN derived sensory features and the resilience of AVSR systems to noise by performing isolated word recognition tasks. Tests on this system showed that combining audio and visual data using MSHMM led to improved recognition rates, especially in noisy environments, with the multimodal approach outperforming unimodal ones at various noise levels. The study revealed that even with the inclusion of noise, the MSHMM model enhanced word recognition by 10% at 0 decibels SNR, indicating the benefits of integrating multiple data streams over using single stream inputs. The number of mixtures in the GMMs had a minimal impact on performance, underscoring the robustness of the multimodal method in speech recognition tasks under different conditions of audio quality. In AVSR experiments of the second paper, the visual data's impact was tested, particularly under poor audio conditions. The comparison of HMM subscript AV and BRNN subscript AV models with either traditional or Gabber features demonstrated the BRNN subscript AV model's superior performance, specifically using Gabber audio and visual features. The BRNN subscript AV model notably improved word recognition, lowering the word error rate from 12.09% to 7.82%. Performance graphs showed that AVSR models integrating visual data outperformed audio only models, especially in noisy environments. For instance, under a negative 10 decibel SNR, the BRNN subscript AV model achieved a substantial reduction in WER or word error rate, emphasizing the advantage of combining audio and visual cues in speech recognition systems. And that is it for my paper review presentation on deep learning based audiovisual speech recognition or AVSR systems. This has been Justin Guzman, and thank you for listening. Have a great day.